Alright guys, so in this lecture we will be talking about energy and chemical bonding, and we're also going to get a start on how to draw these Lewis structures that you guys are going to do for the molecules that we'll be seeing in this chapter. So when we think about chemical bonding, we have to realize that, again, it's not like there's sticks between these various atoms that hold them together, or glue or whatever. But the bonds that we draw, these lines that we're going to be drawing that you've seen before in your sophomore year course, these lines represent energy distributions. So a single line, represents, we call that a single bond, and there's a certain amount of energy that's distributed between those two molecules. Whereas a double bond or a triple bond, would represent different quantities of energy. So because of this, and because we use these bonds as a way to denote how the energy is distributed in a molecule, we can actually use these bonds in a chemical reaction. We look at the bonds that are broken, we look at the bonds that are formed, and we can get a change of enthalpy for the whole reaction, based on the bonds that are broken and reformed. Keep in mind as we're doing this that to break a bond requires an input of energy, and therefore it would be endothermic, and making a new bond actually stabilizes things, and that's an exothermic process. So as far as signs go, any bond that we have to break will have a positive enthalpy change, and any bond that gets formed will have a negative enthalpy change. In your textbook, there is a table, it's table 8.4, and table 8.4 has a series of bond types in it. So when we get to these Lewis structures and you start drawing them, you're going to notice that in the in the model or notation that we use for Lewis structures, that we use lines to denote shared electrons, and as such, a certain amount of energy between those two molecules, or sorry, between those two atoms. And so this table provides you with a series of bond energies, for different combinations. Obviously, there's more types of bonds than just these that can form, but this gives you a good start for a lot of the molecules that we'll be looking at. Notice kind of down here for CO2, it has its own little special bond energy. So if you ever have a C double bond to an O in CO2, that's going to have a slightly different bond energy than what's shown up here. Okay. So as I said, we can use these bond energies to calculate the heat released or absorbed in a chemical reaction. And what we do is we take the sum, and so this is the summation sign right here. Okay. So you take the sum of the bond energies of all the bonds in the reactants that are being broken. Okay, so as we go from reactants to products, bonds are going to have to be broken, and bonds are going to be reformed. So the bond energies for all of the bonds we have to break get added together, and those are going to be positive. And then we subtract from that the bond energies of all the products. So the products, when products are made, we form new bonds, and that's why we have a negative sign. This negative sign right here comes from the fact that the bond energies of products are exothermic, and therefore we give it, we give it a negative sign to denote heat leaving our system. So to see how all this is put together, okay, we can look at a fairly simple reaction, and what we want to do is we want to calculate the change of enthalpy for the reaction between nitrogen and hydrogen to make ammonia. Okay, ammonia is right here. Okay, now we've learned how to do this before using Hess's law. We've learned how to do this using heats of formation. Now we're going to learn how to do this using bond energies. And so in order to do this successfully, we first have to know what the bonds are in each of these molecules in this reaction. In other words, how many single bonds of each type, how many double bonds of each type, how many triple bonds. So nitrogen has a triple bond between the other nitrogen. Okay, so that is what a nitrogen molecule is symbolized as, is having a triple bond between the two nitrogens. And then we have 3 hydrogen bonds, and the hydrogen bond is a single bond between the two hydrogens, and that's going to go to form 2 ammonia molecules. Now in the ammonia molecule, there's 3 single nitrogen hydrogen bonds in each molecule. Okay. And if we go back to that table from bond energies, okay, so from that table I just showed you, table 8.2, we can say that the nitrogen-nitrogen triple bond has an energy of 941 kilojoules per mole. The hydrogen-hydrogen single bond has a bond energy of 432 kilojoules per mole. And the nitrogen-hydrogen bond energy has an energy of 391 kilojoules per mole. So when it comes to time, when we want to find the delta H for this whole reaction, once again we'll take the sum of the bond energies from all the reactants. So bond energy from reactants, and subtract from that the sum of the bond energy from the products. Okay. So let's go ahead and get started. We have the nitrogen-nitrogen triple bond is one of our reactants, and so we only have one molecule, so that'll be 941 kilojoules. Okay, I'm not going to put the per mole here because we're kind of multiplying it by 1 mole of nitrogen, so that's going to go away. Add to that 3 times, because we have 3 molecules, 3 times the bond energy of hydrogen-hydrogen, which would be 432 kilojoules per mole, and eventually that mole is going to go away because we're multiplying by 3 moles. And when we do that, we're going to get 2,237 kilojoules. Okay, so that's how much energy needs to be put in to break all those bonds in the nitrogen and hydrogen molecules. Then on the other side, we have 2 ammonia molecules, and each one has 3 nitrogen-hydrogen bonds. So we're going to be forming 6 new bonds altogether, and each bond will have an energy of 391 kilojoules, okay, per mole. Multiply by essentially 6 moles, and we would get 2,346 kilojoules. And you put that together, and we would get negative 109 kilojoules, and that will be the change of enthalpy for our reaction. Okay. So once again, this provides a third way to get the change of enthalpy for reaction. The first 2, remember, were Hess's law and using heats of formation, and now we can use bond energies. Now this relies on you forming, being able to realize the bonds that are going to be, that exist. In other words, going from these molecular formulas to these structures with the bonds in them. And so that's what the next lecture will be about.